Hello, and welcome to this demonstration of Icon Science's RokDoc software. Today, we'll be focusing on the rock physics module, an industry-leading toolkit that provides best-in-class advanced rock physics modelling functionality and workflows. We'll be looking at a near-field exploration setting, where offset well data will be used to investigate the seismic amplitude response at a prospective target location. The main RokDoc project view provides an overview of the loaded data via a basemap interface. In order to perform robust rock physics analyses, geological, geophysical and engineering data is required. All of this data can be loaded into RokDoc either from industry standard external formats or directly from Schlumberger's Petrel software via Icon's two-way interconnector. Any number of wells, seismic surveys or geological models can be loaded into RokDoc. Here we have a number of regional exploration wells, an appraised oil field, as well as a seismic survey including multiple volumes and horizon interpretations. This is a regional interpretation that corresponds to the top of a thick marine shale sequence. This unit is of fairly uniform thickness at the available well penetrations, so can be used as an indication for the top of the sand-prone unit across the volume. The prospect itself is located in the west. A sand channel was encountered by a well to the south of the prospect, and this had a thin oil column at the top of the sand. There is a suggestion of a trend up to the prospect in the seismic response, but this is not clear and it is uncertain whether the oil encountered in the exploration well is connected up dip. Here we will look for answers to these questions by turning to rock physics. The rock physics workflow shown here represents the first stage of the quantitative interpretation or QI workflow. Let's start by looking at the data from one of the offset wells. This is the RokDoc well view, which allows the display of all data loaded for a particular well. This can include both continuous log data as well as discrete data points such as core analysis or direct pore pressure measurements. The viewer is flexible in that tracks can be added and resized, logs can be dragged and dropped into tracks from the tree, and multiple logs can be included in each track. Color fills can be set up either based on sample by sample value or to a constant value. Annotations can be added to any track. Working intervals can be set up either based on formation tops, a cutoff based on a log, for example volume of shale, or a combination of the two. Here we have a number of working intervals already defined which correspond to our formations of interest in this basin and for this age. For this particular case study, the reservoir is formed of slightly cemented sands with a thick marine shale caprock, and a high oil saturation was encountered in the reservoir sand in this exploration well. The geology in these intervals is described by the petrophysical interpretation, a key input into any rock physics analysis. These describe the geology in terms of volume fractions, porosity and saturation. The other key input into a rock physics analysis is the elastic log data, being P and S sonic logs, and the bulk density log. The sonic logs are used to determine P wave and S wave velocity, or VP and VS. These are the three parameters measured downhole that describe the elastic properties of the rock. Rock physics is the connection between the geology, as described by the petrophysics, and the elastic properties of the rock as measured by the elastic logs. Once we understand the elastic properties of the rocks, we can start to investigate the seismic responses. Any other continuous log data can be loaded. Here, for example, we have resistivity logs and neutron porosity. Check shots are also available and can be used to calibrate a depth time conversion for the well. Further work on a quantitative well tie will be performed later. Understanding the quality of the available log data is key to the success of any rock physics analysis. The data needs to be understood in terms of its quality and consistency. If any issues are detected, remedial steps must be taken, and it is important to set expectations as to what can be achieved with a given dataset at the start of any study. RokDoc provides the tools to perform user-friendly log conditioning both easily and thoroughly. Issues with log data may be the result of the effect of borehole cavings on the elastic log measurements, mud filtrate invasion replacing the in-situ fluids, or other log issues such as cycle skipping in sonic log measurements. Here we see the dcal log, which is the caliper minus bit size. This indicates overgauge hole, with a high frequency oscillation in this case. It can be seen that this oscillation affects the other log measurements. Here this effect is too small to be of much concern, but is illustrative of how log data can be rapidly compared and QC'd using the well viewer. The other way of assessing log data quality is via crossplots. Here we have P wave velocity, VP, plotted against bulk density for the intervals of interest. This is coloured by volume of shale. The data can be compared to published reference trends. Here contours of constant AI are also shown. Histograms for each variable can be shown. The data can be coloured by any log type, by row or by working interval. The data can be sampled in any Z-stick, for example, measured depth or two-way time. Point density can also be plotted, which shows the number of points falling in each histogram bin. Here we can see data points with high bulk density relative to their p-wave velocity. These can be selected in the plot and highlighted in the well view, and you can see that the VP does not resolve the stringers seen in the bulk density log. This can be corrected by predicting VP for these stringers based on the bulk density, for example. Often shear sonic data is not logged, or when it is logged it is of variable quality depending on the nature of the formations of interest. Therefore, the ability to predict VS log data can be key. RokDoc provides a number of methods by which the shear behaviour of rocks can be predicted. These include both empirical trend-based approaches and calibrated rock physics models. We will have a quick review of the empirical approaches. Individual trends between VP and VS can be used, or a method where n-member trends are weighted based on the volume fractions in the petrophysical interpretation. These trends are generally applicable to brine-saturated rocks, as mixed saturations result in deviations in the trend, and this is the fluid effect. Where mixed hydrocarbons are encountered by a well, and a VS prediction is required, methods such as modified Gaussian can be used. This attempts to estimate the fluid effect before removing it, predicting VS, and then finally replacing the fluid effect. This employs a modified linear version of Gaussian's equation. VS predictions can be made per working interval, with QC logs and a final VS prediction saved. A key step in rock physics is the identification of seismically distinct rock types. These elastic lithofacies classifications form the basis of rock physics analyses, and the aim is to understand the seismic expression of each of these units. The first step is to classify the elastic responses for the rocks encountered by the offset wells into discrete, elastically distinct units. We will base the classification in the acoustic impedance and VP-VS ratio responses using a clustering approach. Clustering is a technique that is used in a variety of data analysis situations. Its basis is to place members into distinct groups, searching for the maximum homogeneity in each group and the maximum differences between groups. A Gaussian mixture approach is taken to this clustering analysis. The algorithm is iterative and converges to an optimum based on the posterior probability that each member sample belongs to its assigned cluster. This method provides output logs containing the probabilities of the assignment of each sample to each cluster. The classification of the elastic log response can be compared to the petrophysical interpretation. The final classification can be shown via a series of QC crossplots. Here we identify brine-saturated sands in yellow, oil-saturated sands in green, a cap rock shale in purple, and an intra-reservoir shale in grey. One important step in a rock physics analysis can be the prediction of the elastic properties of rocks for fluid saturations other than those encountered by the wells. We therefore need to be able to perform fluid substitution. In clastic rocks, we commonly turn to Gaussian's equations. These fluid relations allow us to perturb VP, VS and ρB data to be representative of an arbitrary fluid saturation. In RokDoc, we provide a dry rock modelling step to the fluid substitution problem, where mineral and fluid properties are used to determine a dry rock response. Including a dry rock QC and potentially modelling phase has two benefits. Firstly, the dry rock response implied by the petrophysics, elastic logs and assumed mineral and fluid properties can be sense checked. And secondly, a dry rock model can be optionally imposed. In this case, the dry rock model is used to limit the fluid effect in slightly shaly sands. It can also be used to control the fluid effect where elastic log quality issues persist. A dry rock Poisson's ratio versus porosity plot is provided for additional QC. Any saturation can be modelled using this functionality, with perturbed VP, VS and ρB data saved as a set. For this example, an 80% oil saturation has been modelled in the sands. A close match is observed where there is high in situ oil saturation in the upper sand. In the brine-saturated deeper sands, the difference is more marked. The modelled logs for each fluid saturation can be overlaid in each track, with different colours specified for each fluid case. As before, logs can be dragged and dropped from the tree and added to any track and compared for QC and comparison purposes. In this example, the brine-saturated case is compared to the oil-saturated case. Next, we should take this data and generate AVO reflectivity models. In order to generate synthetic AVO gathers from elastic log data, an upscaling step is required to ensure that the reflectivity models are consistent with the rock unit that the seismic responds to. Upscaling is an important step at many points in the rock physics workflow. We will look at backwards averaging. where the elastic moduli of the rock are upscaled over a sliding window before the velocities are reconstructed. This approach also provides estimates of Thompson's anisotropy parameters. Next, we will take the elastic log data and generate AVO reflectivity models. These are mostly based on a 1D convolution of a wavelet with an angle-dependent reflectivity series. The reflectivity can be based on a number of different reflectivity equations. A full waveform option is also provided. Any available wavelet may be used. These may be reference Ormsby, Butterworth or Ricker wavelets, statistical wavelets extracted from seismic data, or the result of a quantitative well tie. A number of 2- and 3-term reflectivity equations are provided, as well as other methods such as the full waveform approach. A fire angle for the gather can be specified, and once it's calculated, it is shown in the gather track in the well view. As with all other tracks in the well view, these gather tracks are flexible in that they can be moved and resized within the view. Once synthetic gathers have been generated for a number of scenarios, they can be displayed within the well viewer and amplitudes extracted at any interface. The AVO response at the top of the sand unit is now being shown, and the AVO is plotted in the lower attribute plot. Multiple gather tracks can be shown with different fluid cases in each. The brine and oil saturated cases are shown now. The extracted AVO for the top of the sand can be compared between the cases in the attribute plots, which show amplitude versus angle here. We can also generate single interface or half-space AVO models. These are based on average values extracted from different intervals at the well locations, or from analog data. Multiple interfaces can be defined, and AVO responses for each plotted. Here we see the shale on brine sand and shale on oil sand case. A number of different reflectivity equations are again provided, and the horizontal axis can be changed to show either theta, sine theta, or sine squared theta, which is useful for plotting linearized AVO from a 2-term reflectivity equation. It is also possible to plot these linearized responses in terms of intercept and gradient, and to plot them on an intercept gradient crossplot. The constant values used to build these models can have a mean and standard deviation associated. This allows simulations to be run to get an idea of the spread of each response. A further option is provided to generate a projection attribute in intercept and gradient space. At this stage, we have identified the key and elastically distinct lithofacies, we have modelled fluid saturations other than those encountered by the wells, and we have generated AVO reflectivity models to help us understand how AVO changes as a function of different fluid saturations within the sands. We may wish to extend the modelling to include other scenarios not encountered by the wells. For example, we can perform lithology substitution by adjusting porosity or compaction state. One way to do this is using a calibrated rock physics model. Here we have a crossplot of P-wave velocity versus porosity for the reservoir sand facies. A rock physics template can be added to the plot, and here we are plotting a model that relates geological properties, including porosity, mineralogy, and compaction state, to elastic response. The model is calibrated to the data based on a number of parameters. These can be adjusted, and the template will automatically update to reflect the changes. In this way, we can model the effect of these geological properties on the elastic response. The elastic properties of the non-reservoir facies may be captured based on depth trends. RokDoc's depth trend analysis tool is ideal for capturing depth dependency in various geological and elastic properties. The analysis can be done in a multi-well sense, per working interval, with trends referenced to a selected marker or datum, and the spread of the data can be captured. The trends can be defined per facies. Here we see the VP versus burial depth for the shales. The datum for the trend can be updated using a drop-down menu, and the Z-stick is automatically updated to account for the change. The trends themselves can be saved as rock physics models and can be output to a trend well for use later. The rock physics model outputs can be combined with the depth trends into any kind of 1D, 2D, 3D or 4D model within the various RokDoc modules. For example, the outputs have been used to define a pseudo-well at the prospect location. A number of scenarios can be compared to the seismic response. In this instance, a brine and an oil-saturated reservoir sand have been generated, but any number of scenarios can be developed, for example with different sandstone porosities or compaction states. In this pseudo-well, anisotropy has been included in the cap-rock shale interval in some of these models, and this has been done using RokDoc's anisotropy add-on. In many basins and in many intervals, anisotropy can be a key control on the AVO response, so needs to be investigated. Please see the accompanying video for more information on this add-on. We should review the impedance responses of the facies of interest, and this forms a well-based inversion feasibility analysis. In this case, we would like to establish which attributes can be used to extract more information from the seismic data. Tools for both the analysis of absolute and relative impedances are provided within the RokDoc rock physics module. A cross-plot of acoustic impedance versus VP/VS ratio is shown for each of the facies of interest, and a rock physics template overlain to provide geological context. The data should be reviewed at both log scale and seismic scale, as the averaging of the seismic response can change the trends observed between the facies. The histograms provide information regarding the overlap of facies in each elastic property space. We should also review relative rock elastic properties, as these can be more directly related back to the observed seismic amplitude response. Ball et al. Proposed a new approach to the calculation of relative rock properties in 2014, and this workflow has been implemented within the rock physics module. Furthermore, a relative EEI projection tool has been implemented that takes the outputs of the relative rock physics workflow and allows the investigation of projections based on the relative elastic properties. We will look for projections in relative AI and relative GI space. Any combination of relative elastic properties could be used. A correlation to any relative petrophysical attributes can be made, with a projection log shown interactively in the track. Here a projection of around 30 degrees should provide a good prediction of water saturation from relative elastic properties. We can define a similar projection to maximize lithology effects. This type of workflow allows us to investigate useful impedance attributes that can be inverted from the seismic data. We can generate these attributes at the wells at both seismic and log scale to understand how any impedance attribute would respond to the layering at each well. The last step in this workflow is to perform a quantitative well tie. Knowledge of the seismic wavelet is a key step in understanding the geological signal within the seismic response. There are multiple ways to estimate wavelets from seismic data in RokDoc. Within the rock physics module, functionality is provided to estimate wavelets directly from the seismic data using a frequency domain least squares approach. The well tie is considered a noisy input, noisy output problem, and this is consistent with the work of White 1990 and Walden and White 1998. The process involves the use of a reflectivity spike series based on the elastic log data and a trace extracted from the seismic data. There must be consistency between reflectivity and trace in terms of the seismic attribute and angle. The aim is to capture the seismic bandwidth within the wavelet while avoiding fitting to noise. This process is controlled by the analysis window T and the wavelet analysis length L. All relevant parameters for the wavelet estimation can be specified here, and once the wavelet has been calculated, it can be reviewed in terms of accuracy and goodness of fit. Goodness of fit is normally assessed in terms of PEP, or proportion of energy predicted. Accuracy can be assessed in terms of the wavelet's phase error. Other metrics related to bandwidth and time window used are provided. The wavelet can be reviewed in time, and error bars are calculated for both the amplitude and phase spectra. The phase and timing of the estimated wavelet can be calculated by performing a linear fit to the phase spectra over a user-defined bandwidth. The intercept indicates the phase, and the gradient tells us something about the timing or lag. All metrics for each wavelet are saved along with the estimation parameters and can be reviewed at any stage. Wavelets can be edited in time, or edits can be made to the phase or amplitude spectra. Averages of multiple wavelets can be generated. We have now made a quantitative link between the well data and the seismic response. At this stage, we have determined the facies of interest in the study area and age, performed rock physics modelling workflows on the offset well data, and determined the expected AVO and impedance responses for each facies. Finally, the well data has been tied to the seismic and wavelets estimated. The next stage in a QI workflow would be to invert the seismic data for the identified impedances. The Reservoir Characterization module is an ideal space to perform this kind of work. Please see the accompanying video. Here the attributes identified in the relative rock physics analysis have been generated from the available seismic data, one sensitive to lithology and one sensitive to hydrocarbon saturation. These attributes clarify the seismic response, and it can be seen that at the prospect location both a sand and a hydrocarbon response are indicated. The distribution of sands and hydrocarbon saturation across the volume has also been clarified. A typical rock physics modelling workflow has been shown here, but there are many more options available in the RokDoc software. Please contact info@iconscience.com for more information, or visit our website at www.iconscience.com. Thank you for listening.